module, we are going to see about a specific type of group called the cyclic group and some of its properties. Let us see the definition. A group G comma star is cyclic if there exists an element x belongs to G such that G can be written as the set of all x power n such that n belongs to Z, where Z is a set of integers. So, x power n is equal to x star x so on n times. So, this is the meaning of x power n. In particular, if the star operation that we denote here is denoted by addition, G comma plus is equal to the set of all nx such that n belongs to Z, and this particular group is cyclic if nx is equal to x plus so on up to x, and this operation is done n times, therefore, we get nx. So, G is written as the group generated by the element x. Let us see some examples. The set of integers z comma plus is cyclic because z can be generated by 1 as well as minus 1. For example, if you are considering the element 5 can be written as 1 plus so on 5 times. If you add them 5 times, you get 5. Similarly, minus 5 also belongs to the set of integers, the negative integer group. So, this can be written as minus 1 plus so on up to minus 1 5 times. So, we can say that z comma plus is cyclic, and these are the two generators. Now, Zn comma addition modulo is cyclic. Here also 1 and minus 1 are generators where minus 1 is equal to n minus 1. Now, we consider the unitary group U10 that is equal to 1, 3, 7, 9. We can easily see that it can be generated by 3 as well as 7. Now, if you take 3 power 0 is 1, 3 power 1 is 3 cube is 27, but when divided by 10 you get the remainder 7, 3 squared is 9, again you get 9 here. So, 1, 3, 7, 9 can be generated as the powers of 3. Likewise, for 7, it is 7 power 0 is 1, 7 cube is 343, again when divided by 10 it is 3, remainder is 3, 7 power 1 is 7 and 7 squared is 49. So, the remainder is 9. So, 1, 3, 7, 9 again can be generated by 7. So, the generators of U10 are 3 and 7. Now, we shall see some theorems. Let G be an element of a group G. Then there are two possibilities for the cyclic subgroup generated by G. Case 1, the cyclic subgroup is a finite group. In this case, there exists an integer n such that G power n is equal to 1, and these three properties hold. A, G power k is equal to 1 if and only if n divides k. B, G power k is equal to G power m implies and re-implies k is congruent to m mod n, and point C, the group generated by G is equal to 1 G squared so on up to G n minus 1, and all these Gi's are distinct. Now, let us see the proof. Since we say that the set G or the group generated by G is 1 G squared so on up to G n minus 1, and it is finite, the powers G squared so on etc. are not all distinct. Suppose they are not distinct, then you can find an element G power k and G power m such that they are equal, and with k less than m. If this is true, then this implies that G power m minus k is equal to 1, where m minus k is greater than 0. So, this implies that there exists an integer L such that G power L is equal to 1. So, we have proved the existence of such integer. Now, let n be the smallest such integer such that G power n is equal to 1. Now, these are the assumptions for this theorem. Now, let us dive into the theorem. The first point, G power k is equal to 1 if and only if n divides k. Now, let us assume the first part. If n divides k, then k can be written as Qn for some q belonging to the set of integers. Then G power k is equal to G power Qn, and this can be written as g power n the whole power q. Now, we have already said that g power n is equal to 1, and therefore, this is equal to 1 power q and this is equal to 1. So, we have proved one part of the theorem. So, we assume that n divides k and we proved that g power k is equal to 1. Now, coming to the converse part, let us assume that g power k is equal to 1, then k can be written as qn plus r. This is according to the division algorithm, where r lies between 0 and n. G power k minus qn. So, r is equal to k minus qn from here. So, g power r is equal to g power k into g power n the whole power minus q, and we already know that g power n is equal to 1. We have assumed that g power k is also equal to 1, and therefore, this will give you 1. Now, this is creating a trouble for us because r is a smaller integer than n. That is our assumption according to the division algorithm, and this is a contradiction because we have assumed that n is the smallest integer for which g power n is equal to 1, and therefore, this cannot be true, and therefore, r is equal to 0 and k equal to qn, which implies n divides k. So, we took proof by contradiction and we have proved the statement. Now, coming to point B, if we have g power k is equal to g power m, then k is congruent to m mod n. Now, all we have to do is take g power k is equal to g power m, and from this we can write g power k minus m is equal to 1, and now we know that from point A, g power k is equal to 1 if and only if n divides k. So, we can say that if similarly we are applying point A here, so we will get this is true if and only if k minus m divides k. Now, we prove point number B, which is g power k is equal to g power m if and only if k is congruent to m mod n. So, suppose we have two elements g power k and g power n, and both of them are equal. This implies that g power k minus m is equal to 1. All we have to do is apply point A, which is g power k is equal to 1 if and only if n divides k. So, similarly, if you are going to apply this to point B, then we will get that this is true if and only if n divides k minus m according to point A. Therefore, k minus n divides k minus m implies that k is congruent to m mod n. Now, we shall prove C. We are going to show that the group generated by G, that is 1 g, g squared, so on up to gn minus 1, they are both equal. So, we are going to prove that the group generated by G is of this format, and all these elements here are distinct. Let us assume this particular group first. So, 1 g, g squared, so on up to gn minus 1. Now, this is clearly a subgroup of G. So, it is very obvious. So, let us stop there and mark it as equation number 1. Now, let us go on to the other side of the set inclusion. So, let us take an element A belonging to G. In this case, A is of the form g power k for some k belonging to Z. So, k is equal to qn plus r, where 0 less than or equal to r less than n minus 1. So, this implies that A is equal to g power k, that is equal to g power qn plus r. So, that is equal to g power n the whole times q times g power r, and this is equal to 1 power q, because we have assumed already that g power n is equal to 1, and therefore, wherever you have g power n you can substitute 1. So, 1 power q is again 1, and now g power r. Now, we know that g power r is belonging to this particular set. So, we have taken an element A belonging to this particular set, and we have proved that it is of the format 1 g, g squared, so on up to g n minus 1, and therefore, the other part of the set inclusion has been proved, and therefore, we can say that G is a subset of 1 g, g squared, so on up to g n minus 1. So, from 1 and 2 you can say that group generated by G is equal to 1 g, g squared, so on up to g n minus 1. The second part, we have to prove that these GIs are distinct. So, let us assume that they are not distinct. In that case, there will be some g power k and some g power m, so that both of them are equal. So, g power k equals g power m implies that there is 0 less than or equal to k less than or equal to m. So, this is less than or equal to n minus 1. So, g power m minus k is equal to 1. So, from here you get g power m minus k is equal to 1, and this m minus k is less than n. Now, this violates our previous condition, that is G power n is equal to 1 and n is the smallest integer for which this particular statement is true. That was the original assumption. So, this particular statement is violating our condition, and therefore, we can say that this is a contradiction, and therefore, our assumption is wrong, and this implies that m minus k is equal to 0. So, since m minus k is equal to 0, we can say that GIs are distinct, and that proves point C. Next, we shall see the case 2, in which case we will be discussing the cyclic subgroup generated by G when it is infinite. And therefore, the group generated by G is infinite, and these are the three properties here. So, property A, G power k is equal to 1 if and only if k is equal to 0, and property B, G power k is equal to G power m if and only if k is equal to m. Then C, G is equal to G power minus 3, G power minus 2, G power minus 1. So, there is a distinction between finite and infinite case where you have powers or negative powers here, and here also the GIs are distinct. So, these are the three properties. So, we will prove property number A. So, G power k is equal to 1. So, the first part is obvious because this is k equal to 0 is true, anything to the power 0 is 1. Suppose you have G power k is equal to 1 and k is not equal to 0. So, either k can be less than 0 or k can be greater than 0. So, G power minus k will become G power k the whole power minus 1. So, 1 power minus 1, again it becomes 1. So, G power n is equal to 1 for some n greater than 0. So, this is the conclusion that we make from here. But this will violate a condition that G is infinite, because when you have G power n is equal to 1 for some n greater than 0, this will imply that G is finite, and hence a contradiction arises, and therefore, our assumption that k is not equal to 0 does not hold. So, k only has to be 0. So, this is part A. Part B, the property B, if G power k is equal to G power m. Now, this is true if G power k minus m is equal to 1. So, all we have to do is apply A here, and therefore, you will get k minus m is equal to 0 or k is equal to m. So, B is proved. Now, when we come to C, so G has G can be written as G times k, where k belongs to Z. All you have to do is apply B here. So, already we have proved B, that G power k equal to G power m if and only if k is equal to m. So, you need to prove that the GIs are distinct. Suppose they are not distinct and you have two elements which are having the same value, and you have G power k equal to G power m, then obviously k is equal to m. That is what we have proved in B. So, from B we can say that C is true. So, C, the GIs are also distinct. So, with this we have proved the properties for the infinite group, cyclic group, and you can notice that there is a distinction between the finite and infinite group. So, there G power n is equal to 1 if and only if n divides k you had. So, the cyclic property of n comes in. Here we have, because it is an infinite group, you have k equal to 0. There G power k equal to G power n if and only if k is congruent to m mod n we had, but here k should be equal to m, and here only thing is that there will not be any negative powers for a finite group. Here we will have negative powers, and it goes on infinitely on both sides. So, that is the main distinction between a finite and an infinite cyclic group. Next, we shall see a very important theorem in cyclic groups, namely every cyclic group is isomorphic to Zn or Z. So, we know that there are two types of cyclic groups, namely finite and infinite cyclic groups. So, obviously, cyclic group, if it is finite, it is going to be isomorphic to Zn, and if it is infinite, it is going to be isomorphic to Z, because Z is infinite and Zn is finite. Now, let us go to the proof. Suppose G is a cyclic group, then G is written as the group generated by the element G, which is inside G itself. So, all the elements of the form E, G, so on up to G power n minus 1. So, for the first one, we are going to cover the finite case. So, when we are covering the finite case, then there is going to be an element n, a positive integer n, such that G power n is equal to E. One additional property is that this n is the smallest positive integer for which this particular statement is true, and G can be written as E, G, G squared, so on up to G power n minus 1. So, this is a finite cyclic group. and we are defining a function f from Zn to g by f of m is equal to g power m. So our objective is to prove that this particular function is a isomorphism. So in order to prove that this is an isomorphism, we will be proving the 1-1 property, onto property, as well as that it is an homomorphism. So the homomorphism will be proved like this. So f of m1 times f of m2, that is equal to g power m1 times g power m2. So this is the definition, and therefore we are just applying a definition here. So this is equal to g power m1 plus m2. This is equal to g power m1 plus m2 mod n. So from part B of the previous theorem under the finite cyclic group, we have already proved that there is a cyclic number involved. So this cannot, there will be a repetition otherwise. Therefore m1 plus m2 mod n, and therefore this is equal to f of m1 addition modulo m2. So from part B this is obvious, and therefore we have now proved that the homomorphism property holds. Now to prove the 1-1 property, let us assume that f of m1 is equal to f of m2. We have to prove that m1 is equal to m2. Now this implies that g power m1 is equal to g power m2, where m1 and m2 are elements in 0, 1, 2, so on up to n minus 1. Why is this? Because we know that the elements of G are of the form E, G, G squared, so on up to G power n minus 1. You can clearly see that the powers are either 0, 1, 2, so on up to n minus 1 here, and therefore whatever be the powers here, m1 or m2, they are going to belong to this particular set only, 0, 1, 2, so on up to n minus 1. Now from this statement, we get that G power m1 minus m2 is equal to E. Now this is a contradiction because we have only now said that n is the smallest integer for which g power n is equal to E, and m1 minus m2 is going to be smaller than n. Therefore, this particular statement cannot be true because it is a contradiction to our assumption, and therefore this can only mean that m1 minus m2 is equal to 0, and therefore m1 is equal to m2. So we started at f of m1 is equal to f of m2, and we ended at m1 is equal to m2, and therefore we have cleared 1-1 property. The onto property is pretty obvious because we have assumed that f of m is equal to g power m. So whatever be the powers of g, so E, G, G squared, so on up to g power n minus 1, definitely going to be a pre-image in the form of m. So if there is g power g squared, there is going to be 2 here in the domain. So it is obvious that it is onto. Now we have checked the properties for homomorphism, 1-1 and onto property for a finite cyclic group. Similarly, for an infinite cyclic group, we are considering the same property only here. So same function f z to g is defined by f of m is equal to g power m. So the initial assumption is that because it is infinite, there is no n such that g power n is equal to E, or in other words, g power n is not equal to E for all n belonging to z plus. So let us check for the homomorphism property. So f of m1 plus m2 is equal to g of m1 plus m2, that is g of m1 times g of m2. This is obvious because it comes straight from the mapping itself. So f of m1 times f of m2, therefore homomorphism property holds. 1-1 property, again f of m1 is equal to f of m2 with m1 greater than m2 implies g of m1 is equal to g of m2. So this implies g of m1 minus m2 is equal to E. So this is not possible because it is a contradiction to our original assumption that g power n is equal to not equal to E for all n belonging to z plus. Therefore this is not true, and therefore we can say that, so f of m1 is equal to f of m2 implies that m1 is equal to m2. Similarly, onto property, again by the virtue of the mapping, f of m is equal to g power m, and again here also it is very clear that whatever be the element in our infinitely generated cyclic group, there is going to be a pre-image in the form of the power m, and therefore onto property is clearly holding here, and therefore we have proved homomorphism, 1-1 and onto property. Here also isomorphism holds. For both finite and infinite cyclic groups, we have shown that every cyclic group is isomorphic to Zn or Z. Now let us see the relation between cyclic property and abelian property in the next theorem. Every cyclic group is abelian. Proof. Let G be a cyclic group with a generator G belonging to G. Let A and B be arbitrary elements in G. then there exists some n comma m belonging to the set of integers z such that a is equal to g power n and b is equal to g power m. It follows that ab is equal to g power n times g power m, that is equal to g power n plus m. So, since addition is abelian, we can write it as g power m plus n, and that is equal to g power m times g power n, that is equal to ba. So, we have now proved that AB is equal to BA for any arbitrary element A comma B belonging to G, and therefore, G is an abelian group. We shall now see the next theorem. Let A be an element of order n in a group and let k be a positive integer. Then the group generated by A power k is equal to the group generated by A power GCD of n comma k, and the order of A power k is equal to n by GCD of n comma k. So, this is the statement here where k is some positive integer. So, the proof, let d be equal to GCD of n comma k. Now, since d divides k, you can write it as k equal to d into r, where r is some integer. Therefore, a power k is equal to a power d the whole power r. So, we can write it like this, which implies that the group generated by a power k is a subset of the group generated by a power d. So, this is because a power k is equal to a power d the whole power r. So, we have brought it to this form, that is why we are able to write this statement, and therefore, a power d is equal to a power ns plus kt. Again, this is from this assumption d is equal to GCD of n comma k, and therefore, this is possible. So, d can be written as ns plus kt, where s and t are some integers. Therefore, this can be written as a power ns times a power kt, which is equal to a power n the whole times s, and a power k times t the whole power t. This is equal to, now a power n is equal to e. This is the primary assumption here. Therefore, this is equal to e, a power k the whole time t, which is equal to a power k the whole power t, and now this is of the format a power k the whole power something. So, this element obviously belongs to the group generated by a power k. We have brought it to this format, and therefore, we started at an element that is a power d, and it belongs to a power k, the group generated by a power k, and therefore, we can show that a power d is a subset of a power k, the group generated. Both the groups are subgroups of each other, and one part we have already proved here, that is the group generated by a power k is a subgroup of a power d, and from these two statements we can say that the group generated by a power d is the same as the group generated by a power k. And the second part is, we need to prove this statement, the order of a power k is equal to n by GCD of n comma k. So, for that, let us assume that, let us first prove that the order of a power d is equal to n by d for all d. Now, d is GCD of n comma k, I am just looking back to it. Now, clearly a power d the whole power n by d will be equal to, so the d will get cancelled and you will have a power n, which is equal to e. So, which means that we know by the definition of order that this particular term n by d should be the order of this element, which implies that order of a power d is less than or equal to n by d, again by the definition of order. Suppose that then there exists one I less than n by d, which implies that a power d is a power d the whole power I is not equal to e. This is because we have assumed that a power n is equal to e, and n is the smallest integer for which this is equal to e, and therefore, there can not be an I such that which is less than n by d, for which this statement is true, and therefore, we can say that a power d is equal to, the order of a power d is equal to n by d. So, we have proved this part, and by applying our original statement, that is d is equal to GCD of n comma k, we get order of a power k. Now, I am going to prove this part. Order of a power k is equal to the order of the group generated by a power k, which is the same as the order of the group generated by a power d. Now, this is from this statement, a power d, the group generated by a power d is the same as the group generated by a power k, and therefore, the orders are going to be the same, and this is equal to this. And now, but we have only now proved that the order of a power d is n by d, and therefore, that is equal to n by GCD of n comma k, because d is equal to GCD of n comma k. Now we have proved the statement of this theorem. Now let us solve some problems by using the previous theorems. Problem number 1. Find the order of the element a power 32 in the cyclic group G equal to 1a, a squared, so on up to a power 37. So clearly the order is 38, n is equal to 38 and k is equal to 32. By the previous theorem, we have to find the GCD of 38 and 32. This is equal to 2 and therefore a power 32 has the order n divided by GCD of n comma k. We just found the GCD of n comma k to be 2 and therefore the order is 38 divided by 2, which is equal to 19. Similarly, we will do problem number 2. Find the order of the element 18 belonging to Z30. So the group is of order n is equal to 30. The element 18 belonging to Z30 corresponds to A18 in the previous theorem. So k is equal to 18 and the GCD of 18 comma 30 is 6. So 30 divided by 6 is 5. The order of 18 is 5. Now we will do problem number 3. Prove that any group of prime order is cyclic. Now let G be a group whose order is a prime number p. Since p is greater than 1, there is an element A belonging to G such that A is not equal to E. Now the group A generated by A is a subgroup of G. So we are going to use Lagrange's theorem. So we know that the order of a subgroup divides the order of the group. So order of A divides order of G, but the only divisors of G are P and 1. So since A is not equal to E, 1 won't come and therefore we will have order of this group generated by A will be greater than 1 and therefore order of the group generated by A is equal to P. So from this we can say that the group generated by A, which is equal to G, is cyclic. So the following theorem will give an idea to find the generators of a cyclic group. Theorem, let the order of A be equal to n. Then number 1, group generated by A power I is equal to the group generated by A power j if and only if the GCD of n comma I is equal to the GCD of n comma j. Number 2, the order of A power I is equal to order of A power j if and only if the GCD of n comma I is equal to GCD of n comma j. Property 3, the group generated by A is equal to the group generated by A power j if and only if the GCD of n comma j is equal to 1 and the order of A is equal to the order of the group generated by A power j if and only if GCD of n comma j is equal to 1. Now let us see an example that will clarify the concept of the last theorem. Let us consider the group U25. We know that this group is consisting of the elements which are relatively prime to 25. So you can see that the elements are 1, 2, 3, 4. We do not have 5 because 5 and 25 are not relatively prime. So we have 6, 7, 8, 9, 11, 12, 13, 14, 16, 17, 18, 19, 21, 22, 23 and 24. So the order of 25, U25 is equal to 20. Now U25 can be generated by the element 2. By previous theorem, we are going to find the other generators of this particular group. Now we need to find those elements which are relatively prime to 20. So 2 power 1 mod 25 is 2, 2 power 3 mod 25 is 8. So we are picking those elements which are relatively prime to 20. Therefore we are picking the elements 1, 3, 7, 9, 11, 13, 17, 19, 21 and 23. So in all we will have 8 generators, namely 2, 3, 8, 12, 13, 17, 22 and 23, and we use the previous theorem to find this result. So U25 can be generated by 2, 3, 8, 12, 13, 17, 22 and 23. Next we shall see a theorem. Every subgroup of a cyclic group is cyclic. Now the proof is, if G is a cyclic group, then it can be generated by an element G inside G, and therefore this is G is equal to the set generated by the element G, and this is of the form G power k where k belongs to Z. Now let H be a subgroup of G. Then if H is equal to the identity element E. So, if H is a trivial group, then obviously H is cyclic. So, let us assume the non-trivial case. In this case, let G par K belong to H with G par K not equal to 1. Then since H is a subgroup, G par minus K is equal to G par K the whole par minus 1, and therefore, now closure and inverse property has been satisfied, and they belong to H, and therefore, H is a subgroup. Let G par K belong to H with G par K not equal to 1. Then since H is a subgroup, G par minus K is equal to G par K the whole par minus 1, which belongs to H. So, we have proved the subgroup property. Therefore, since K or minus K is positive, H contains a positive power of G not equal to 1. So, let M be the smallest positive integer such that G par M belongs to H, then certainly all powers of G par M are also in H, and therefore, we have the group generated by G par M is a subset of H. We claim that this inclusion is an equality. To see this, let G par K be any element of H. Recall that all the elements of G and hence H are powers of G since G is cyclic. So, by division algorithm, K is equal to Qm plus R, where 0 less than or equal to R less than M. So, G par K is equal to G par Qm plus R, that is equal to G par Qm times G par R, that is G par M the whole par Q into G par R. Now, if you were to take this G par R to the left hand side, it becomes G par R is equal to G par M the whole par minus Q times G par K, which belongs to H. Now, from this we can say that R can only be 0, because G par M the whole par minus Q times G par K is written like this, and therefore, G par K is equal to G par M the whole par Q, which belongs to G par M, the group generated by G par M. So, already we have proved that the group generated by G par M is a subset of H. Now, we have taken an element from H and we have proved that it is of the form G par M the whole times something. Therefore, it definitely belongs to the group generated by G par M, and now we have shown that H is a subgroup of G par M, the group generated by G par M. From these two statements, we can show that H is equal to the group generated by G par M. So, we have now proved our statement that the subgroup of a cyclic group is also cyclic, because we have shown that they are of this form G par M. Clearly, they are cyclic elements. Now, the next theorem states that Zm cross Zn is cyclic if and only if M and N are relatively prime. The proof: suppose M and N are relatively prime, then the least common multiple of M and N is Mn. Consider the element 1 comma 1, then K of 1 comma 1 is equal to, then K times 1 comma 1 is equal to K comma K, which is equal to 0 comma 0, if and only if K is a multiple of both M and N. Since Mn is an LCM of M comma N, it is the smallest power of 1 comma 1 that equals the identity element. Thus, the order of 1 comma 1 is equal to Mn, so that it is a cyclic subgroup that is the same size as the full group. Therefore, it is a whole group and Zm cross Zn, and so Zm cross Zn is cyclic. Now, suppose that the GCD of M comma N is equal to D. Then Mn by D is less than Mn, and it is the LCM of M and N. Now, let R comma S be an element of Zm cross Zn, and note that Mn by D times R comma S is equal to Mn by D R comma Mn by D S, which is equal to 0 comma 0. So, all the elements of Zm cross Zn have order less than Mn, which is the order of the full group. So, none can generate the group. Some of the examples are as follows. Consider the group Z2 cross Z3. This is of the form, the elements are of the form ordered pairs M comma N, such that M belongs to Z2 and N belongs to Z3. So, 1 comma 1 plus 1 comma 1. So, we are going to find the order of this group. So, 1 comma 1 plus 1 comma 1. So, 1 plus 1. So, which is, we will be following Z2 operation for the first element of the pair and Z3 operation for the second element of the pair. Therefore, 1 plus 1 is 0 for the first element and 1 plus 1 is 2 for the second element, because we are following Z3 for the second element. Now, this 0 comma 2 we are going to add with 1 comma 1 again, and doing the same type of operation here we are getting 1 plus 0 is 1, 1 plus 2 is 0, because for Z3 you do not have the element 3, it becomes 0. Then similarly that 1 comma 0 we take and we add with 1 comma 1, that is 0 comma 1. Similarly we get this 0 comma 1 is added to 1 comma 1, we get 1 comma 2. So, 1 comma 1 plus 1 comma 2 is 0 comma 0. So, we found that you have to add 1 comma 1 6 times in order to arrive at the identity element, and therefore, Z2 cross Z3 is a cyclic group of order 6. You can see that all the elements of Z2 cross Z3 are also present here. So, clearly the order is 6. The next example is we are going to consider the cyclic group Z42, and we are going to generate all the cyclic subgroups of Z42. They have been represented in a table format in the screen. In this module, we studied about a special type of group called the cyclic groups. We saw about finite cyclic groups and infinite cyclic groups. We saw that the finite cyclic group is isomorphic to the group Zn, and we also saw that the infinite cyclic group is isomorphic to the set of all integers Z. And one more theorem we saw was every subgroup of a cyclic group is cyclic, and we also saw about Zm cross Zn is cyclic if and only if m and n are relatively prime. These are some of the results we discussed in this module. We also saw some of the problems related to these theorems. I hope that this was useful to you. Thank you.